Hi, I'm Katie with Bridge Gap, and today we are going to be learning about functional groups and IUPAC naming. Last lesson in organic chemistry, we started on hydrocarbons and looking in how to name hydrocarbon alkanes, alkenes, alkynes, and substituents. So today we're going to talk a little bit more about that, practice some, and get into some other functional groups. So let's get right into it. First, I'm going to talk about the IUPAC naming rules. These are something that throughout all of organic chemistry you're going to want to keep in mind. So number one is to count the carbons of the chain. So you're going to have a chain of carbons, those little zigzag lines like this, and you're going to want to count those. And when you have a substituent, whatever this is going to be, you're going to want to count so that the substituent is the lowest number possible. So I know common sense tells you we go from left to right when you're reading on a page or something like that. In this circumstance here, instead of starting at the left, you're going to start here on the right so that your substituent is at the lowest number possible. So 1, 2, 3, 4, 5, 6. And then number 2 here is going to be just what we did and talked about in the last lecture, which is naming that root chain. So here, you know your suffix is going to be ane. Since there's no double bonds, no triple bonds, it's all single bonded carbons. You know your suffix is going to be ane. And since there's 6 carbons, this is hexane. So that's your first step. The third step is going to be identifying the substituents. So last time we looked at hydrocarbon substituents, and you already know how to name those. So if you have a molecule and that's your substituent, you know that this is a methyl. And that's your substituent. In the rest of this lecture, we're going to talk about what to do if your substituent isn't just hydrocarbons. Sometimes you'll run into substituents that repeat. So here, if we had this and we had 2 methyls here, how do you name that? It's going to be dimethyl. And we're going to go examples. This is all going to make a little more sense. This is just some things to keep in your mind. And then as you're putting it all together, once you kind of go through those pieces, you're going to list the substituents in alphabetical order. So for example, if we had a molecule that looked like this, and we had a isopropyl there and a methyl here, you're going to put isopropyl first and methyl second. There are some caveats to this that can get a little bit confusing. And based on your organic chemistry teacher and your exams, they might not be super picky on this because it can get a little controversial, I guess I would say. Normally, you're not going to count, like if I have a dimethyl, I'm not going to count that di. So it's not going to go by the D in the alphabetical order. It's going to go by M for methyl. Similarly, if I have like a tert butyl group that looks like this, I'm not going to count that tert. It's going to go by butyl, so it's going to be B in the alphabetical order. Also, when you're numbering them, normally the way I like to think about it is if you have a double or a triple bond, that kind of acts like a substituent in a way when you come to numbering and naming, and we're going to do some examples. This will make a little bit more sense here in a second. But I like to kind of consider those double and triple bonds as a substituent. In that circumstance, since those get incorporated into the suffix of that root name that we talked about up here in number 2, since the name of double bond and triple bond is incorporated into that root name, the number goes before that root name. It's not going to be alphabetized, if that makes any sense. So these are just things to keep in mind as we move forward. So here I have some examples, and these are all hydrocarbons from last lecture that we talked about. So I'm going to walk us through some of these. We'll start with this first one up here in the left-hand corner. So first step is to number the carbons. And like I said, you want a number so that the substituent is on the lowest number carbon possible. So I'm going to start on this side so that the substituent is first. So I'm going to start over here. 1, 2, 3, 4, 5, 6, 7. So this has 7 carbons. So we know that our root prefix is going to be hept. And we see a double bond, so it's going to be ene. So we know that's our root is heptene. That's our first couple steps. Now we're going to identify our substituents. So right here, we have 1 carbon coming off. So that's a methyl. And here we have that double bond. Like I said, I kind of count that as a substituent just because you do have to indicate where it is in the naming. And we did go over this last lecture too. So if that's confusing, go back and watch that again. But here, the name of this is then going to be 3-methyl 4-heptene, since that double bond is on the 4th carbon. I'm going to move on to the next example now. So we're going to start numbering again. 1, 2, 3, 4, 5, 6. This is all single bond, so this is going to be hexane. And here we have an isopropyl group. So it's going to be 3 isopropyl hexane. Next example. Here you can see we don't really have any substituents coming off. It's just that triple bond. So this is how we have to number the carbons so that that triple bond is the lowest, kind of like the substituent. So we're going to start on the right-hand side once again. It's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. And with the triple bonds, you draw them straight across like that. I know it can get a little bit confusing with the number of carbons there. That's the way the triple bond will act in space. Because of all those bonds stacking up, it makes the molecule a little bit more rigid. So in organic chemistry, we draw it straight across instead of the zigzag lines like the single and double bonds. Just a little side note there. But here, it's not going to have any other substituents. So this is 3 non, because 9, and then ine for the triple bond. Moving on to our next example, we have some rings. So you can start anywhere on the rings if there's no substituents like this first one down here. So we'll start with 1, 2, 3, 4, 5, just numbering. And in this circumstance with the rings, all you do is add in the prefix cyclo. So since there's no substituents and no double bonds, this is going to be cyclopentane. Pretty simple there. Next one, we're going to start numbering so that your double bond is the lowest, just like a substituent. So you can kind of start on either side of the double bond and go work your way around in this circumstance. But I'll start here. 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be octene. Since there's just that one double bond, we don't have to indicate one octene. It's just there on the first one. It's understood that way. And then our last one here, there's 3 double bonds, so they're all kind of equal in weight. They're all the same substituent here. So we're just going to start 1, 2, 3, 4, 5, 6. So then this is going to be 1, 3, 5, hexene. And this is also known as benzene. That's the common name for it. But there you go, that's how it looks. So this next page here gets a little bit more complicated. I'm gonna try to go through these quickly, and I'm not gonna go through all of them. I'm just gonna go through some, and then you can pause it, try to finish the rest on your own as practice, and I'll just skip ahead to the answers. So with the ring here, you're gonna start in, so the substituents are on the lowest amount. So 1, 2, 3, 4, 5, 6. So this is hex. All single bonds. Ane. You know, there's going to be a cyclo in the front here. I'm going to move that over to there. And then here we have 1, 2, 3. So this is a propyl. And here we have a methyl. So you put them in alphabetical order. So we have, even though the propyl's on the 1, the methyl comes first in the alphabet. So it's 4-methyl, 1-propyl, cyclohexane. And I'll move on to this example and then I'll pause and you guys can do the rest on your own. So here you can see it's kind of confusing because if you start in from the right, 1, 2, you have that methyl as the second. And here it's 1, 2 if you start from the left and you have the double bond. So sometimes you're going to run into this where you have to decide what you prioritize in the naming. Typically, bonds are always last, and we're going to get into this as we get into other functional groups. The whatever comes first in the carbons, that's going to be first before any of the bonds. And as we get into the functional groups in a second here, you're going to see I have them listed in the order of their priority. So there's a very specific order of naming that you use, and that's the order the numbering goes as well. So it can get a little tricky. It's a lot of rules that you have to follow, but to me it makes a lot of sense, and it's really not too complicated. So in this circumstance, we are going to start from the right-hand side, and we're going to number these. And then we'll identify our substituents. So on the second carbon here, we have a methyl. Down here, we have a sec-butyl. And you can count those just to double check. 1, 2, 3, 4 carbons. And then we have those 2 double bonds. So this example, it's a non-ene, because there's 9 carbons and there's 2 double bonds. And those double bonds are on 3 and 7. So 3, 7, non-ene. And then our butyl, even though that sec is there, the butyl comes first in the alphabet. So it's going to be 5-sec-butyl, 2-methyl, 3,7-nonene. So you guys can pause the video here, write these down, try to work on the next ones on your own. But just for time's sake, I'm going to keep moving on. So I just wanted to take a second to sort of review something that you should have learned back in general chemistry, normal general chemistry classes, but it's sort of a key part of organic chemistry. And to me, it's something that really, really helps me remember what to do if I'm kind of stuck of like, how does this molecule work? How do I put it together? So I wanted to take time to review it here, and I did go a little bit into this in the last lecture with just carbon. So if you remember, I talked about how carbon has 4 valence electrons, and so it always likes to have 4 bonds around it. Normally, in the most basic sense, that's hydrogen, but it can be other things as well. And what this is all based on is something called the octet rule. So in all times, your sort of center atom, and every element really, is going to want to have 8 electrons around it to satisfy that octet. So with the hydrogens and the carbons, hydrogen's the outlier, and it doesn't want an octet. It only wants like 2 because it only has 1 to share. So hydrogen offers 1 electron, and then that carbon has 4. And so total, if you kind of count those bonds as 2 electrons, you have 1, 2, 3, 4, 5, 6, 7, 8. So that satisfies the octet rule. So carbon, to keep it happy, keep it within its octet, it's always going to have 4 bonds. Hydrogen's always going to have 1 bond. As we move in away from the hydrocarbons into more functional groups, oxygen is different. Instead of having 4 valence electrons, it has 6. So looks like that. 6 valence electrons, but we need 2 more to get to the octet. So what it's going to do is it's going to bind to something to share their electrons and pull it off of them in order to have 8 to make it happy. So oxygen likes 2 bonds, and that can also look like this with a double bond instead of 2 single bonds. So normally when you see oxygen, it'll be attached to two other things, and or it can have just one double bond. If it has any more than that, that's wrong. It doesn't work that way. Oxygen doesn't like to be that way. And with nitrogen, it's in the 5th group of the periodic table, so it has 5 valence electrons. And so in order to fulfill its octet and make nitrogen happy, it has 3 bonds. So that can look like this with 3 single bonds, or it can have a single bond and a double bond, or it can have a triple bond. So that's something that you're going to see a lot, and you're going to see this in your functional groups as well. So this is moving on with the IUPAC naming. So that's what we just did with the hydrocarbons and their substituents. Now we're going to briefly talk about the IUPAC naming with functional groups, and also just learning on how to identify them. So I have these listed in order of their IUPAC priority. So like I said, when you're numbering or whatever the suffix is, if there's multiple of these in a structure, the suffix is going to be based on their priority on this list. And I know it kind of seems intimidating, but for me it makes a lot of sense, and I'm going to try to really make this chart something that's useful to you guys instead of just like, oh my god, I have to memorize this. So the first one here we have is a carboxylic acid. And like the name suggests, this is an acid. So that's one of the properties that this molecule has, and that's something that as you get into organic chemistry will make a little bit more sense. But it has here the OH on the end and then a double bonded O here. So that's always connected, those two right next to each other. That's a carboxylic acid. And the suffix when you're naming this is oic acid. Moving on, we have an ester. So it's sort of the same thing as a carboxylic acid, except instead of the OH on the end, it has an OR. So it's going to be connected to some other carbon molecule is what that R means, instead of a hydrogen. And it also has the double bonded O right next to it as well. The suffix when you're naming this is going to be O8. I remember this sort of underneath it is like your carboxylic acid. That's such like a fancy name. That's sort of the top of the list, #1 priority. The ester is like the closest variation you're going to get of that, with just that carbon instead of the hydrogen, if that makes sense. Then moving down, you have aldehyde. And the suffix for this is Al. To me, the suffixes are probably the easiest part of remembering these. Aldehyde, Al at the end. And so it's sort of going down that list. Now instead of the OH, you knocked off that H, you just had the O and some carbons. Now you're knocking off that O and you just have a hydrogen. So it's just going to be that double bonded oxygen on an end of a molecule where that hydrogen is. A lot of the times students will get confused with this because people will draw it like that. And it's just understood that there's a hydrogen here, but they won't draw it in. And so people will get a little confused, and they'll confuse it with the next thing, which is a ketone. But you have to remember that that hydrogen, when it's this carbon here in the middle, has that hydrogen there. It's just understood because carbon always has those 4 bonds to fulfill its octet. So it's a little bit tricky, but once you can identify that, it's not that hard to keep straight in your mind. And the next one's the ketone. So the ending for that is -one, ketone. The ending's -one. Not that hard to understand. And it's kind of like with the carboxylic acid, you had the OH. Then with the ester, you had the OR. Then with the aldehyde, you just had the H. Now you just have the R. So it's that same sort of pattern. That is the way I like to think of it to help you remember. That's the order that it's in. So now it's going to be a double bonded oxygen, but it's going to be in the middle of a molecule instead of on the end. So there's going to be carbon chains or rings on either side of it. Next, you have an alcohol. So the ending of this is OL, just all, like alcohol. And this is just an OH. So now instead of having like an oxygen on its own and a double bond, you got rid of the double bond completely, and now we're just going down to the OH. So you can see how it is kind of like decreasing in like the amount of oxygen, or the power that oxygen has, is the way I like to think of it. And you will learn more about the properties of these functional groups, and that'll make a little bit more sense as well. But that's your alcohol. And then you move on to nitrogen. So you have an amine, which is a nitrogen that's connected to just other carbons or hydrogens. So all of these R groups that I have here, those can be carbons or hydrogens. Any amount of carbons or hydrogens, but there's no oxygen directly next to that nitrogen in the amine. You can kind of remember that just because the amine has an N, so it's just kind of nitrogen. And then next you have an amide with that double bonded O coming back. So it's kind of building back up to the amide. And it adds in that double bonded O, and that's right next to the nitrogen. And once again, these R groups here could be either hydrogens or carbons. And then last is an ether. And the reason this one is down at the bottom is because it's technically not considered in IUPAC naming as a suffix. It's always considered a substituent. And how you name that is based on this R group here. So like if this is your big molecule, and then this is normally going to be just like a tiny one, it's going to be a substituent, and that's going to be what you base it off of. So if this was like I have a butyl here, it would be butyl ether, just as an example. And we'll get into the naming more in a little bit, but that's why it's at the bottom. To me, I like to kind of consider an ether as like a brother to the ester, just because their names sound the same and they were very similar. They're easy to get mixed up. For me, how I like to consider it is this one here, the ester, has more O's, and the O's kind of look like Easter eggs. So more O's, Easter, ester. That's sort of the thing in my mind that helps it make sense. But once again, as you practice, this will be second nature. It's not going to be super, super intimidating as it is now. But this is something that you guys will need to know. Highly recommend making flashcards or something to try to really get this down and understand how it works. And we are going to move into examples, not naming yet, just identifying what these functional groups are. So I'll start with this molecule here. And I also just wanted to add, I know last time I talked about how molecules look really scary, and that's why a lot of people don't love organic chemistry, or why they're afraid of it. I feel like the second reason is because people are like, why am I ever going to need to know this? I just have to take this class in school. This doesn't matter. And I use these examples because organic chemistry does matter, and it's a very vital part of literally everything. So this molecule right here, that's my first example, is serotonin, which some of you may have heard of. It's often referred to as like the happy chemical. It's a neurotransmitter in your brain. So, this is an organic structure. We're going to practice with it, and it's something that's literally in all of your heads right now. So that's why I like to use some of these examples, just because they're to make it fun and to remind you guys that organic chemistry is like a real thing that's happening in our bodies and in the plants and nature and the drugs that scientists make, and it's a really cool science, and it's not just something that you have to take in school. So anyways, off of my rant, moving on. We're just gonna circle the functional groups and identify them in these examples. So we'll start here with this, which is an alcohol. Here we have an amine, and you can see with this amine, it just has those two hydrogens on the end. Those could be carbons as well, but in this circumstance, they are hydrogens. And down here, we have another amine. So, lots of fun. We'll move on to the next example. So here we have an ether. This right here is our benzene ring that we talked about in the last lecture. Often that's going to be referred to as an aromatic ring, and that'll make a little more sense in following lectures as we learn about aromaticity. But sometimes when you are practicing and you're identifying functional groups, professors might refer to that as sort of its own functional group, a big ring with all those double bonds, and they might just refer to it as an aromatic ring. So just something to keep in mind. Here we have another ether and an alcohol and another alcohol. And this example, I forget what structure this is that I pulled. Oh, this is the drug that's in Mucinex. So when you get a cold, this is what helps you get rid of it. Lots of fun. So this next example here, again, we're just identifying the functional groups. This example of the bigger molecule is lisinopril. That's a very common blood pressure drug. Some of you guys might be on it, your parents, but you can see functional groups are a big part of the drugs we put in our body. So here we have a carboxylic acid. Here we have that benzene ring. Right here's an amine. Another amine down here. Right here we have an amide, and that's because that nitrogen is right next to that double bonded O. And up here we have another carboxylic acid. And then I'll move on to my last example down here. This is actually a compound that's in cilantro that often makes it taste like soap. A lot of people say cilantro tastes soapy. This compound, that's why. See, how fun. But this is kind of a simple one, you may think, but I'm gonna give you guys a second. I'm gonna pause here and let you guys identify the functional group. So I'll give you a second. And this is an aldehyde. So if you said ketone, I'm so sorry, you are wrong, but this is an aldehyde, and that's because you don't have to draw in that hydrogen there, but there is a hydrogen. So that is all the time we have for today, and thanks for watching. Have a good day.